Everybody for coming to the second annual Elizabeth Meckes Memorial Lecture. This lecture series was established not just to honor Elizabeth's memory, it was actually, as some of you know, her own brainchild. Elizabeth loved mathematics. Even more than that, she loved the intellectual community that the university represents. Mathematicians, of course, take part in that community through our research and our teaching, but Elizabeth wanted to see us have a more active role in the general intellectual conversation. And to that end, she envisioned having the department bring in excellent mathematicians who are also excellent speakers to give a public lecture and share with students and scholars from across the university the beauty and the intellectual draw and the fun of mathematics. And today we have Elizabeth's own PhD advisor, Professor Percy Diaconis, here to do just that. So, tell you a bit about our speaker. Professor Diaconis' highly distinguished academic career began when he dropped out of high school in order to tour the country with the renowned magician Di Vernon. He spent 10 years working as a magician with a talent not only for sleight of hand, but also for inventing magic tricks based on mathematics. I've heard different versions of what follows, but one version of the story goes that he discovered that he lacked the mathematical background to read the preeminent treatise on probability theory, and at that point decided he'd better go to college. That started him on a path that led through a PhD in mathematical statistics from Harvard to, cumulative 50 years on the faculties of Stanford, Harvard, Cornell, and back at Stanford, where he is now professor of mathematics and the Mary V. Sunseri Professor of Statistics. Over his career, Percy has written nearly 300 papers in a wide range of fields within mathematics and statistics, and several books, most recently, The Mathematics of Shuffling Cards. If any of you have ever heard it said that to properly mix up a deck of cards, you need to shuffle it 7 times, Percy's the guy who figured that out, actually proved that as a theorem. His work has been recognized by a MacArthur Fellowship, 6 honorary degrees, and too many other honors to list right now. His academic legacy also includes advising nearly 60 PhD students, including our own Elizabeth Meckes, who completed her thesis under his supervision in 2006. If Elizabeth had been able to be here, she would be the one giving this introduction instead of me, and so I want to finish this introduction with a few things that Elizabeth had to say about Percy. Elizabeth described Percy as a wonderful advisor who led me to beautiful mathematics. She said that she asked him to advise her because he seemed like someone I'd enjoy talking to once a week for a few years. Elizabeth credited Percy not only with introducing her to random matrix theory and many other things, but also with teaching her both to enjoy mathematics and to tell a good story. The latter is a talent of Percy's that we will all get to enjoy today. And lastly, with Google's help, you can still locate Elizabeth's personal webpage, where you will see that she said, "Percy's fun. You should talk to him sometime." We're all very fortunate to have the opportunity to do that today.
Thank you. Thank you, and I guess this is good afternoon. Is that what you say at this time? So I'm honored to be part of something that was important to Elizabeth, and let me tell you my story. So I work in the mathematics of randomness, probability and statistics, and they're everywhere in science and business and engineering and just every part of any time you look at the real world, there's noise, and how do you describe it and what do we do about it? It's important to remember that probability began from the analysis of games and gambling. Now, people, probabilists don't like to remember that, but it's true. And so I have spent my life thinking about things like, when you flip a coin, is it actually fair? No, it's not. It's kind of chance of, when you flip an actual coin, so the chance of it coming up the same way it started is about 0.51. So that's funny a little bit. Mark said, how many times do you have to shuffle a deck of cards? And bridge players hate me, but the answer is 7, and it's sort of tedious. And so on. So you can look at the uses of probability in the world and try to think about them theoretically. What I want to talk to you about today is one of the embarrassments of my subject. So it's the bottom line is, we can't figure out what the odds are of winning at solitaire. Now, millions of people play solitaire every day. I mean, you see them on their phones, on their computers, and when they think you're not looking, there they are, right? And now solitaire, the version I'm going to talk about is, there's an ordinary deck of 52 cards. They're shuffled up, and then you deal 7 piles, 1 card, 2 cards, 3 cards. The 7th pile has 7 cards. You turn up the top card of each card. There are 24 cards left over. You put them over here. And then the idea is to try to find aces and then play them up, and then find deuces and play them on the aces, and etc. And if you can get all of the cards from the face down piles to the face up piles, you've won. So roughly, that's solitaire. So how many people here have played solitaire? Anybody? Wow. I better be careful in that case. Well, I have something to tell you. We really don't know the answer to the question I asked, and if any of you can figure it out, I promise you, I'll get you on the front page of the New York Times. I'm not kidding. The people actually would like to know, not just in theory, be nice to know. We really would like to know what are the chances of winning at solitaire. Now, when people hear I'm thinking about solitaire, they say, well, can't you do all of that stuff on the computer? It's 2024. Well, let me tell you a story. When I was teaching at Harvard, an energetic young woman, Amy Rabb, came up to me and said, I want to do my senior thesis on solitaire. I said, great, that's a wonderful project. And she came back maybe 6 weeks later, and she'd written a computer program, so this is 20 years ago. It was more of a thing to do, but it could display cards and it could actually play, so you try to, well, I'll explain a little bit more about rules and stuff, but and she was it could play just without her help, and she won about 8% of the games. 8% of the games. And I said, okay, now we're going to do an experiment. We're going to take 100, you can shuffle a deck of cards 100 times and record the order, and then you're going to play, she's a good solitaire player, you're going to play the deck through in solitaire, and then we'll have the computer play the same deck, just to see, whether you can do anything. And the computer won 8% of the time, and she won about 18% of the time. So that's the problem with programming a computer to play solitaire. We don't know how to tell the computer to play solitaire, and it doesn't know how to learn. And even though you think, well, wait a second, it can play chess, it can play Go, it can do GPT chat, of course it can play solitaire. Nah, I'll tell you what the efforts are in that department, but it kind of can't. So, okay, so we're stuck. So what am I going to talk to you about for the next 50 minutes or 40 minutes? Well, I've done what we always do in math, and that's follow Polya's dictum. George Polya is a great mathematician, and he said, if there's a hard problem you can't solve, then there's an easier problem you can't solve. So that's what we do. So here's an easier problem, which we now can solve, but I didn't know that when I started. So I'm going to make something I call simple solitaire. And we have a deck of cards, and N is 52 if you like, but I'm a mathematician, so I'm going to call it N. We have N cards. You could play it with any number of cards. And of course, cards have, numbers and suits, and you have to make an ordering of them. So clubs are bigger than hearts, or bigger than spades, or bigger than diamonds, or whatever you like. And then of course, so I'm going to suppose we have a deck of cards that's labeled 1 up to N. Okay, and you shuffle them up, and there are rules, and these are simple rules. You turn them up one at a time. There are 2 rules. You can play a low card on a high card. I'll do an example in a second. So a 2 on a 6. So if you're turning the cards up and you turn up a 2 and there's a 6 showing, you could put the 2 on the 6. And the only other rule is if you turn up a higher card than any showing, you have to start a new pile. So you turn up a 10 and there's nothing to play it on, you have to start a new pile. And the object of the game is to get as few piles as possible. So let's try an example, because that's the only way to do it. So here's an example with 10 cards. So first I need a random arrangement of 10 cards. Here it comes. One, two, three, four, five, six, 7, 8, 9, 10. Haha. Okay, so that's 10 cards. Is that okay with everybody? So what's that? That's a 6. 6. Okay, so the 6 is on top. So we're going to play solitaire with the deck in this order. This is the top card, next card. So there's the 6 is on top. Then there's the 5. I'll put the 5 on the 6. Then there's a 2. I'll put the 2 on the 5. But then this is a 7. I have to start a new pile. The 4, I can't put it on the 2. I better put it here. The 3, I can put it here. 8, I have to start a new pile. Here's a 1. So I could put the 1 here, here, or here. Right? It's kind of sensible to put it on the 2 because that wastes less space. Right? I mean, somehow if I put it on the 8, then that's killed that pile, and so maybe I'll put the 1 here, and then the 10 certainly has to start a new pile, and the 9 I put here. So we have 1, 2, 3, 4 piles. Okay, everybody got it? That's our simple solitaire, and the object is to get as few piles as possible. Now, I'll tell you a little bit about this solitaire as we go, but it's actually possible to play it if you have real cards, because you don't remember the clubs go on hearts, and if the TV is on and you're watching a movie, you can actually play it. It's not so boring. I mean, it's not as interesting as other games. I am going to talk about real solitaire, but this is a playable version, and it has many other good things to say for itself, as you'll see. So that's our simple solitaire. So I suppose you had to decide things. So what's the chance of getting only one pile? How could you get all the cards just in one pile? Well, the only way that could happen is if, suppose it was with 1 up to 10. If 10 is on top, and then you play it, and then 9 is next, okay, put it on the 10. And if they're in order, 10 up to 1, then you'd have one pile, right? That's pretty rare that the cards are exactly in order. If you had n cards, it's 1 over n factorial, and when n is 52, n factorial is 8 times 10 to the 68th, which is, if all of the atoms in the universe were little computers, they could never run through all arrangements of a deck of cards. So the chance is infinitesimal of having one pile. What's the chance that the worst thing happens and you have n piles? Well, if card 1 is on top, and 2 is next, we'll have to start a new pile, and 3. So that's very rare too. So if you play, you have some number of piles between 1 and n, and it's definitely between 1 and n. And how does it go? Well, nothing stops me from trying it on the computer. And so the first thing we did when we wanted to know the answer to this question, how many piles is typical when you play this simple solitaire? I'm using the rule play as far to the left as you can. So we, with a deck of 52 cards, we played it 100,000 times. The computer played it 100,000 times, and I want to tell you the numbers, and here they are. So, well, the best that happened with 52 cards is once, a few times we got 8 piles. This is the number of piles. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. The worst that happened is we got 18 piles once. Okay, that happened once. This happened 64 times. This is the number of times it happened. This is, 55 times. This is 1,745. This is out of 100,000 tries. So you could just try it out and see what happens. How many piles do you get when you play this solitaire? And it was a summary is, roughly between 10 to 13 piles, and 9 or fewer around 1 in 20. So 0.05 is a number we use. So maybe you say, well, you win the game if you get 9 or fewer piles. So you don't win too often, and you could make your own choices. So that's the kind of, you try it out and see how you do. That's a thing. That's your thing you do. Okay, so that's the start of simple solitaire, and so. I want to remember this is a math talk, not a card shuffling talk. That's this afternoon. So let me tell you about something called L of pi. Pi is a permutation, and L of pi is equal to the length of the longest increasing subsequence in pi. So here's a permutation. Where is it? This one. So what's the longest increasing subsequence I can make? Well, here's 2, 4, 8, 10. Let's try that. 2, 4, 8, 10. That's an increasing subsequence of length 4. 1, 2, 3, 4. You won't find another one that's longer. You can look, there are other ones, you could try, 5, 7, 8, 10, but you won't find one longer than 4. So L of pi is the length of the longest increasing subsequence in pi. Why am I telling you about that? Well, it's a famous thing in some corners of the mathematical world. This is called Ulam's problem, Stan Ulam. And it connects to solitaire, because here's the one and only theorem I'm going to be able to prove about any kind of solitaire. So let me be proud of it and call it theorem. The number of piles is always bigger than or equal to L of pi, and if you play to the left, you get L of pi. And so L of pi is the answer to how many piles are there going to be if I play through this deck And you don't have to play through the deck. You have to figure out what L of pi is anyway. And I'm not going to do anything like this for the rest of the talk, but I'm going to do it right now. I'm going to prove this theorem. I hope you follow. I'm going to prove it the way I prove theorems in the air. So suppose you're playing the solitaire game, and suppose there's an increasing subsequence of length 4 in the deck someplace. There's a deck 1 up to n, some crazy order, and then there's an increasing subsequence, maybe not even the longest one, okay? Okay, so 3, 7, 12, 14, I don't know. Okay, so now you're playing solitaire, and then you turn up card 3, it goes someplace, right? The only cards that can go on the pile that has 3 in it are lower values. And so none of the cards that come later that are in the longest increasing sequence can go on that pile. Right? So maybe 3, 7. So then you keep dealing, then the 7 comes up. It can't go on the 3, so it goes someplace. None of the cards that are below it and that have bigger values can go on that pile. So however you play the solitaire game, if you have an increasing subsequence, you have at least that many piles. That, I hope, makes sense to people. So the number of piles is bigger than or equal to L of pi. Now, in the other direction, so what I try to argue is the number of piles in any way of playing, stupid, clever, is bigger than or equal to L of pi. Okay, now in the other direction, for play to the left, okay, so you played the solitaire game the best way you know how, and there you are. So there's the last card that you put on. You have some number P of piles, say 18 piles, I don't know. The last card you played on the last pile, remember you're playing to the left, the last card you played on the last pile, the reason you played it on that last pile was because when you played it, all of the cards that were showing were lower than it. So that means in the pile just before the last pile, that the top card, there's a card that came before that card, which has a lower number. And take that card. When you played it, the cards that came before it, that you could see, also, they all had lower numbers. So in the pile just before it, there's a lower number. And you keep going. And what you can see is that you constructed an increasing subsequence, which is the length of the number of piles. So if you play to the left, the L of pi, the longest increasing subsequence is certainly bigger than the number of piles. Well, it's bigger than, it's less than, it's equal. So, okay, we proved a theorem. Okay, that's a theorem, tiny little theorem. So therefore, there are theorems to prove in solitaire, and there are theorems to prove in solitaire. So now, again, if you're a certain kind of mathematician, me, it's now, there's a math problem. Okay, this is what's called Ulam's problem. So shuffle a deck of cards, pick a permutation at random, pick an ordering of 1 up to n at random. How large is L of pi for typical permutations, and how does it fluctuate? And it's one of the most elegant and important areas of my field of probability, the study of the length of the longest increasing subsequence, believe it or not. So here's a theorem, it's called the Bike-Deift-Johansen theorem. Those are 3 people, Jinho Bike, Percy Deift, Kurt Johansen. The probability, the chance that, so how large is L of pi typically? Well, it's around 2 times the square root of n. And if you how does it fluctuate around its typical value? It's a funny exponent. It's n to the 1/6, and the chance that that's less than or equal to x tends to a limit when n is large, some f of x. So what that says, I know that not everybody here is a card-carrying mathematician. What that says is that typically L of pi is 2, first of all, 2 root n. So when n is 52, well, root n is 7, something like that, about 7. And 2 root n is 14, right? So L of pi is something 14, 15, and then, of course, it's not always that, and it fluctuates, but the fluctuations are funny. That n to the 1/6 is a very funny exponent, and the chance that the difference between where it should be centered and its standard deviation is, that difference is less than or equal to x, tends to a limit if you play with enormous decks of cards, and that limit is called the Tracy-Whittem distribution. Tracy-Whittem. Those are 2 people, Craig Tracy, Harold Whittem. And the reason I allowed myself to tell it to you, first of all, this theorem has shaped my corner of mathematics and Elizabeth's corner of mathematics, and it was proved for the reasons I told you. That is, it was proved to analyze solitaire, not because it's important in physics, not because it's important in natural mathematically. It was proved because people were interested in solitaire. And then it had all kinds of legs. So I want to tell you a little bit about the legs of this theorem. So the thing I'm not going to tell you about very carefully, but if you want to look at it, if you look at the references I handed out, they'll tell you more than you want to know about it. So the same occurs, and what I mean is actually the same. Well, the largest eigenvalue in random matrices So lots of people in all walks of life work with matrices, linear algebra. And suppose you look at a typical matrix, and what I mean by that, if you want to be technical, is fill out the entries of a random matrix with independent picks from the bell-shaped curve, and make it Hermitian. So, okay. Then matrices have eigenvalues which describe how they stretch space and things like that. And how large is the largest eigenvalue of an n by n matrix? Well, it's around 2 root n, and if you divide by n to the 1/6, the largest eigenvalue of a random matrix has Tracy-Whittem fluctuations. The same theorem is true, exactly the same theorem is true if L of pi is the largest eigenvalue of a random Hermitian matrix. Now that may not be your cup of tea, and how about coffee rings? Well, that's not tea either, I know. Unfortunately, all of us know when we are doing something and put a cup of coffee down, sometimes we pick it up again, and there's coffee rings. Everybody knows about coffee rings. Well, okay, nothing prevents us from thinking about coffee rings. So take a coffee ring and subtract off the circle. Okay, just fit a circle. It fits right inside that coffee ring, the best one you can fit. And look at the fluctuations, how much the ring differs from the circle you subtracted off. And make a histogram of those fluctuations. That has these Tracy-Whittem type fluctuations to it. And it's not true for tea, actually. It's true for coffee. And it's both true in the world, that is, it's true if you try it, and it's a theorem also. What else? The same theorem holds for distances between parked cars. So look on a street in Zurich, pick one that you like, and measure the distance. The Swiss are very careful, right? Measure the distances between parked cars. Okay, you could do that. You might get arrested, but and then make a histogram of those distances. They have Tracy Whittem fluctuations. Same for the arrival times between New York City subway trains and the bus times in Cuernavaca, and lots of other things. Now, there's a long list of things that. Yeah. Okay. I put shape of burning piece of paper. Don't try this at home, but take a piece of paper and light the bottom of it on fire. Okay. So up it goes. There's some curve. There's some curve that you can say a typical shape of a curve burning up, and so. And if you subtract out that centering constant and look at the fluctuations, it's Tracy Whittem asymptotics. So. This is a little peek for you at a subject which is called random matrix theory, and Elizabeth Meckes was a great hero of random matrix theory and great contributor, wrote a wonderful book about it and wrote many nice papers. It's a beautiful subject, and it's a strong subject here at Case Western, so you could find out more about it if you wanted to. And this part of random matrix theory began with this thing is called. This question was Ulam's problem. So following solitaire, this simple solitaire led to some very nice mathematics. So, okay, now I want to talk about real solitaire, because what happens from Polya's dictum, you find a problem you can't solve. There's an easier problem you can't solve, and then you get stuck in the easier problem, and you never go back to the actual problem. So let's go back to real solitaire for a few minutes. Let me tell you what we know and how we know it a little bit. So for the rest of the hour, I'll talk about real solitaire. And so remember about real solitaire, 7 piles, and then you could play up aces, and if you have the ace of hearts, you can put the deuce of hearts on it, and there are 24 cards that are left over, and there are different kinds of rules. You can turn them over in threes, you can turn them over one at a time. The version that everybody plays is so-called Microsoft rules, in which you can take some cards from one pile, one of the Talon piles, and put them on others, and turn up a fresh card. Okay, so you don't have to know the rules, but there's very few things you can do at any stage. If you can play a card that's face up on the ace piles, and you maybe want to do that, or you could split piles, or you could try to turn over 3. So suppose you just say, well, there are only a few things I could do. Let me pick something at random, like an idiot. Just play randomly. Just pick something let me pick a random legal move. So random legal. That wins about 7% of the time. So Amy's 8% of the time wasn't actually so good, right? Her fancy computer program wasn't so good. If you're the least bit thoughtful about how you play solitaire, and I'll explain what I mean by that in a minute when I talk about tree search algorithms. Simple rule wins about 13% of the time, and the rule is something like, if you can play a card on the ace piles, play it. Don't. Okay, I'll be. But they're the first thing you would think of. It's better to play a card on the ace piles than to split piles, that kind of thing. Good solitaire players and win about 18% of the time. So Amy was a good solitaire player. Now, how do I know that? Well, I've given this talk before, and like Elizabeth's mom is here, and she's a solitaire player, and so she says she plays every day, so people keep track, or the computer keeps track of how they do, and people who play a lot of solitaire get good at it, and good solitaire players win about 18% of the time. And so that's an empirical, it's not math. I wish I could prove anything like that, but it's true anyway, even though I can't prove anything about it. And now, so let me tell you a story, thoughtful solitaire. So I was giving this talk at Mathematical Sciences Research Institute in Berkeley, and their director is a guy named Irving Kaplansky, who's a great, great mathematician. He came up to me afterwards and said, you know, I play solitaire. And I said, yeah. And he said, and I keep records of how I did. I have records of 5,000 hands of solitaire I played. Well, it's okay. Could I get to see those records? Yeah. And so I went and saw them, and because I'm interested. It's one thing somebody telling you, well, I win about 18% of the time. It's another thing having actual records. And but he played something that he called thoughtful solitaire. And if you're a solitaire player, you might try it. It's pretty interesting. The idea is all the cards are face up. So the 7 piles, you deal them all face up, so you can see everything, and the 24 cards. Now, you may think, well, you can see everything. Yeah. So now what do? Well, I could do this, I could do that. And you start thinking about it. Well, if I do this, then later on I can do that. And it takes about 20 minutes a game to play. It's very different than quickly playing through. And it actually takes thinking, okay? Now, Kaplansky was a great, in many areas, mathematician, and the thought of one of the best American mathematicians, having played 5,000 hands of solitaire, 20 minutes to a half an hour apiece, you start adding up to that. Could have been proving theorems in that time. But meanwhile, so how did he do? So this is now with all the cards face up, okay? So that you see everything, but do the best you can. And he won about 35% of the time. You won't do that with the cards face down, of course, not really. Now, let me tell you the one theorem about real solitaire. Theorem, no algorithm can win more than 82% of the time. So, sometimes you can see, Juliet, Elizabeth's daughter, said to me, well, after 4 minutes you can usually tell the game can't be won. Sometimes you can just see whatever you do, you can't win this game, right? And you can prove that that 18% of all hands are not winnable, no matter how clever you are. You just get stuck. And now, if you're theoretically oriented, let me add a sentence and then a caveat. Deciding if solitaire, real solitaire, with the deck of N cards, is winnable or not. I give you the order, you can look, is there any way you can play that wins? That's an NP complete problem, which means you can't do it. So it's provably an NP complete problem. But I just said we could do it, but I said we could do it when N is 52. The theory of complexity is a limiting theory. It's not a useful theory. Oop. I'm sure I offend some people, but NP completeness has nothing to do with the real world, and scientists in many, many areas have said, yeah, it's NP complete. I compute it anyway for the sample sizes I care about. this is a theorem that no algorithm can win more than 82% of the time. Now, there's a big gap between 18% at good players and 82%, which is the best anybody could possibly do. And where are we in that gap? So I want to tell you a little bit about what the computer can do when it sets its mind to playing solitaire. So it's not that we know, but it can do something. So first of all, and this is as close as we come to my being able to give you any advice at all about how you should play solitaire. So let me explain this simple rule. So as you play, you can assign a score to each possible move. There are only a few moves that you could make. So scoring rules. If you can play on the ace piles, so you have the 7 piles, if you can put a card up onto the ace piles, call that +5. Okay. If you can when you're turning over 3 at a time from the face down 24 cards, when you go through those, and you can take one of those cards and play it on the 7 piles, play on the 7 piles, +5. The rules allow you, and some people think it's, it's worthwhile. The rules allow you to take a card from the ace piles and put them back on the other piles, and then maybe you can shift things around from ace to 7 piles, -10. That's a bad thing to do in this scoring system. Split the 7, so and then k+1. So in the middle of a solitaire game, you have the 7 piles, and you're allowed to take some of the cards which are face up on the 7 piles and put them on other piles, and then turn up a face down card, and that can help because it exposes a new card. And k+1, where k is the number of face down cards. On the split pile. So that might be, if you're not a solitaire player, that's probably hard to parse. But so you might have several things you can do. But if you can, one of the face down piles has 7 cards in it, if you can take some of those cards off and put them here and then turn up one more card, that would get you 7 points, 8 points actually, the way I'm scoring it. And so these are some simple rules that a human can actually use. And if you use these rules playing through, just every time pick the highest score, and if there are two different things you can do and they have the same score, just pick one at random. That strategy gets you 13%. Okay, so now we come to here comes the computer. So enter the computer. So first I'm going to tell you some things that I did in a paper I wrote about solitaire, about Kaplansky's thoughtful solitaire. For thoughtful solitaire. So that is with all the cards face up, but still I have to figure out what to do. Of course, I can use this scheme. That doesn't matter whether the cards are face up or face down. I can use this scheme and just do it. And a thing you can do is, and this is the way that AlphaZero and MuZero, the amazing game playing programs that DeepMind tantalized us all with, and they're all versions of this. So you can roll over the simple strategy. And so what does that mean? So the simple strategy, I haven't said it so explicitly, but you could imagine it's very easy to write down and say as a rule that you can tell the computer to. Here, say X is some configuration and it's just cards and piles and history, and X is just where you are currently in the game, and say the simple strategy has us making some move which I'll call h of x. So in configuration X, the simple strategy says, do this. Okay. And now here's what it means to roll over a strategy. So roll over from X, consider all possible legal moves. So there may be 3 different things you could do from the current configuration. For each, try it. And then use H, the old strategy, as you go on. You already have a strategy, what to do, and just try each of the moves, and then keep playing, keep using the simple strategy. Use H from then on. So suppose that you're doing it in the middle of the hand, right? Suppose you do it and you win. If one move, set one choice wins, change H to H prime, a new strategy which picks this. From X. So of course, to do it once is pretty easy to do, especially if you're playing the game on the computer. But to do it, you have to have a strategy, and then you have to remember what H prime is. H prime is a new strategy, and just okay. So now I have a new strategy which is called H prime, and then you could roll that over. Just start at the beginning and use H prime as your default strategy. Now to do that takes enormous skill at remembering, because X is a configuration of cards. There are a lot of different possibilities. So it takes enormous skill in programming the computer to do that. But you could roll over, and it actually takes a fair amount of time. So with Rabian and Ben Van Roy, we played thoughtful solitaire, rolling over 5 times. It took the computer and clever programming as we could do about an hour and 40 minutes to play each game. It's kind of very inbred and complicated to actually use. But the best rolling over and rolling over, we won about 70% of the time. That's a lot better than Cap's 35% of the time. And so I called him and I said, Cap, we put it on the computer. And really? And I said, well, could I come and show you? Because I was hoping I could get him to play the game and I could get the computer to play with the same hand, with the same deck, and then see what the computer was doing, because God knows what the computer is doing. It's rolling over these strategies inside of itself. We have no way of looking and recording and learning from what it's doing, but it was doing something and it was winning 70% of the time. Well, I went up to see him and he was just awful. He said, you know, this is awful. He said, I spent, thousands of hours playing solitaire, and he said, I thought I played it better than anybody could conceivably play any game. And I really was something that I thought I'd figured out. And he said, you guys killed me. Now, let me just tell you that you may know that checkers, the game of checkers, is a solved game. Nowadays, the computer can play as good checkers as can be played. I mean, we know exactly what the optimal strategy is at checkers. Well, there was a guy, I'm blocking on his name now, but it's not so long ago, maybe 40 years ago, that was the best checker player in the world. He was the best checker player in the world when he was 13, and he never lost a game, okay? And then the computer came, and he agreed to be part of an experiment where there was a $10,000 prize, and they were going to play 100 games of checkers, winner take all, right? Whoever won, take all. Mostly checkers ends in a draw, of course, but okay. The guy in the middle of the match, which had lasted 8 months, because he kept putting it off and saying, I don't feel well today, was down, 4 games to 1 and the rest tied. And he could tell he was going to lose. He was 70 and never lost a game of checkers, and he killed himself. So I'm not making that up, it's true. And his biography was sitting open on Cap's end table. And I thought, Jesus, what have I done? I mean, this is just solitaire, right? And so I agreed to change the subject and talk about something else. Okay, now, so we tell this story in the handout. You'll see a paper that has my name on it with Ben Van Roy and Robbie Jan and somebody else, and the story and all the numbers and the programs are all written down. I'm not making it up. And okay, but that's still thoughtful solitaire. So now it's 2024. I think this happened in 2023, what I'm about to tell you. But so AlphaZero is the program that beat the world's champion at chess, beat all the other chess playing programs, and beat the world champion at Go. And it's just an amazing achievement of computer science. And MuZero is the next generation. First of all, it beat AlphaZero, and it didn't even need to be told the rules. That's the story that you read, right? You could just make it play, and if it did something illegal, well, bad, right? And then it learned to play, and it learned to play very well by playing against itself and being just told what was allowed and what wasn't allowed, but without even knowing the rules. So AlphaZero and MuZero were created by DeepMind, and DeepMind is an amazing company that's based in London, but Google bought them. And there's a big branch of Google in where I am. The biggest branch of Google, I suppose, is near Stanford. And the guy who heads up, there are only 130 PhD engineers in this part of DeepMind, the one at Stanford. But the guy who heads it up is my friend. So I said, I want to try to get the computer to play solitaire, and if you guys can do it, I'll get you on the front page of the New York Times, just like I said to you. And he said, sure, talk to my engineers. And so I got assigned 4 PhD engineers who volunteered, and they were going to try to get DeepMind to, the best programs that we have, to play real solitaire. And the thing that happened, which is fascinating to me, because you think, you just tell it to do it and it does it. And these are people who, that's what they did for a living. And it couldn't do it at all. It couldn't even play through the game once. I mean, it was complicated. It never, they managed to do a six deck a 6-card version solitaire. 1, 2, 3, 4, 5, 6, 2 piles or something. I mean, it was embarrassing, and they tried for several months, and they said, well, we don't know why it is. The final thing I'll tell you about is that there is a team that did it, and didn't do perfectly, but they did something, and that was independent and earlier than DeepMind, and these are these tree search algorithms. So it's the same thing as AlphaZero with a few other bells and whistles. So this is on real solitaire, cards face down. And I just say the numbers a little bit. Well, it has to do with how long you let it run, but okay, so the bottom line can win 34.2% of the time. So the best computer program playing real solitaire can do about as well as Cap did with all the cards face up. This is with the cards face down, and to do this, the program itself took 2,080 seconds per game. It's not so bad. This is tree search algorithms, the kind of thing I outlined here, slightly fancier than what I'm telling you about. So let me summarize and then stop. This is a typical thing that happens to us. There's some real world problem. I think of solitaire. I'd love to be the one who gets on the front page of the New York Times, but it's not going to be me. Excuse me. But there's some real world problem, and we try to think about it, and we can't do it, so we introduce easier problems. And I told you about simple solitaire, play a low card on a high card, and the analysis of simple solitaire led to very interesting mathematics. Some of the deepest mathematics we've done in probability in the last 50 years comes from the work around Ulam's problem. And then I tried to tell you the kind of best we can do. I should put it in here, the best the computer can do. So real solitaire, the best we can do is 34 or so percent. I gave a handout, and I want to just tell you a sentence because there's some wisdom to be garnered from it. First of all, the talk I just gave you, at least the simple solitaire version, if you wanted to look at it, a friendly paper I wrote is with David Aldous. That's under patient sorting. That's what it's called. I didn't tell you this, so let me just tell it to you for a sentence. I see the hour's over anyway, but remember there was the longest increasing subsequence? Suppose you actually want to compute the longest increasing subsequence. Biologists want to do that for DNA string matching algorithms, analogs of that. Suppose, n is 100, and there's an arrangement of a deck of cards. Well, you could try, this is less than that, is less than that. Well, no, but if I put this in, you could imagine it's pretty complicated to compute the length of but you could just play the solitaire game. Right? Just play the solitaire game. Look at how many piles you got. Then you know what the length of the That's provably the fastest algorithm for computing the length of the longest increasing subsequence. And this is some entertainment for a late night around the fire or something like that, I claim that if you actually have to sort a deck of cards, how do you do it? I don't know, how do you do it? Or if you're a teacher and you have to sort 200 blue books, how do you do that, right? I mean, so we have to do stuff like that. So imagine you have 1 up to n, they came in random order, and you've played patient sorting, so there they are. So card 1 is face up someplace, because nothing can go on it. Pick it up. Now card 2 is someplace face up. Pick it up. And card 3 will be facing you, because nothing, only 1 and 2 could go on 3. Pick it up. And if you could just, you sort the cards, just go right through, like, you know, okay. That's why it's called patient sorting. And I claim, that's not a mathematical claim, that that's the physically fastest way for a human to sort n cards, a 52-card deck. And you can, people argue with that, but we've tried it a lot. And nobody seems, in theory, there are a faster way of doing it, quick sort and things like that, but nobody could, a human can't use quick sort. So, okay, so patient sorting is a subject, and I wrote a paper about it, and the reason I'm pointing it out to you is that later, reference 9 there, the American Math Society asked young stars in mathematics to write about a paper that was most influential in their field. And 25 years after our paper, Ivan Corwin, a great probabilist mathematical physicist, said, you know, the most influential paper in my field was Diaconis and Aldis' paper on patient sorting, and then he tries to tell you why. So if you want to see, you know, I'm telling you it had a big impact. It's recorded, if you wanted to know the best possible things to be in for real solitaire, those are in our first few references. For example, my work is reference 4, and that was improved. But the 18% is reference 3, and papers 1 and 2 tell you how fancy versions of this tree search algorithm can give you the best that the computer has done. So this talk was called The Mathematics of Solitaire. I think nobody can argue that I didn't talk to you for an hour about the mathematics of solitaire. Elizabeth thought she wanted people to speak English and talk to people about mathematics. That's what I try to do. Thank you.
Time is well up and the room is crowded, so I think any questions are best addressed in a one-on-one fashion. There will be refreshments in the atrium outside right now. If anybody is in the mood to hear Professor Diaconis give a more technical talk on a different topic in about an hour and a half, we have the Applied Mathematics and Statistics Department colloquium in Wickenton at 3:15. Let's thank first.